Hello. Today's lecture is the tensor product, but I want to say some properties of the tensor product. The main focus is tensor product of the G module, integer module, and universal property on the tensor product, and adjoint associativity. To begin with, let's recall the general definition of the tensor product in the previous lecture 8. Let A be a right-arm module and B is left-arm module over ring R. And F be the pre-abelian group on the set of A product B. That means F is generated by A product B. And let K be the subgroup of F generated by this property. Then the quotient group F quotient K is called tensor product of A and B, which is denoted A tensor product R B. And because F quotient K is clearly vector group, the element of the F quotient K consists of FA, B plus K, and each element is denoted A tensor product B. And this is some properties of the tensor product. In the previous lecture, I referred the general if R is commutative ring, this calculation the properties from 1 to 3 hold, but in case of a general definition of the tensor product, this properties clearly satisfied, and so holds in properties 4. In case of general definition of tensor product, or if R is commutative ring, okay. And the method to these properties arise in K, the properties of the K. So in the previous lecture, when we induced the formula from 1 to 3, I used the properties. The K is generated. K is generated. These three guys. Okay. And what about 4 properties? I did not remark in the previous lecture, but we can prove this here. In order to prove these properties, first we claim, I want to say the equality is A tensor product 0 is 0 tensor product 0. Of course, this 0 we can define 0 tensor product 0 can be written as just 0, and we can prove this equality, and then we can prove also equality. Okay. We know a tensor 0 means a tensor product 0 plus 0. Okay, because the identity properties. And we can, by the properties 2, can expand A tensor product 0 and A tensor product 0. It means, using the definition of the tensor product, this means A comma product is K is equal to, using this expression also, A tensor product K, A comma 0 plus k and a0 a comma 0 plus k. Okay, if with one terms, for example, this terms goes to the left side, by the definition of the quotient group, this is clearly 0, 0 plus k, and this is equal to a plus 0 plus k. Rewriting the tensor notation, this means 0 tensor product 0, and the definition, this is equal to 0, is equal to, this right side is a tensor product 0. Similarly, I induced this equation. Similarly, we can get this equation. Just we can easily induce this equation equality. So we can say this equality, these properties are satisfied. And another notational remark is here. If in case of G module, we can skip the notation this here. This is similarly, we can in case of G module, home RAB is, we can say just home AB if R is equal to integer. And let's see some properties about G modules of tensor product. Let A and B be abelian groups, then a tensor product Gm is isomorphic to a quotient Ma, and Gm tensor product Gn is isomorphic to Gmn. Clearly this is typo, this is n, this is great common divisor. Prior to prove this statement, I introduced the lemma. If we try to this relation, originally we can construct a well-defined map between two groups and check the isomorphism relation, but this is too difficult. But I introduced some lemma to prove easily this statement, but this lemma is also used in the later slide to refer to our main concept, the universal property of the tensor product. So the value of the lemma is significantly meaningful. So let's talk about the lemma. But if you try to this lemma, this is similar if we study the group homomorphism. This lemma is similar to first isomorphic theorism in the homomorphism, group homomorphism. This is very important theorism in the abstract algebra. This is similar version of the group isomorphic theorism, but instead R module homomorphism, just the object is the group homomorphism into R module homomorphism and R module isomorphism. Okay, let's read the lemma. If R is a ring and map F is a homomorphism, R module homomorphism, and C is submodule of canonical F. So in this case, C is subset of the canonical F. Okay, and C is the submodule of the canonical F. If we consider this theorism as the group sense, homomorphism A to B is group homomorphism, and we can consider C is the normal subgroup. This means C is the kernel F. Okay. Then there is the unique R-module homomorphism from A quotient C to B, such that because this is the quotient group, this element is consists of this here, from A to C to FA. If we define the map for all elements in A, this is unique R-module homomorphism. And in order to satisfy bar F is the R-module isomorphism, not homomorphism, is an if and only if. In this case, F is R-module epimorphism and C is equal to kernel F. So if some properties satisfies, then we can deduct A quotient of C is equal to B. And this is, we know in the group sense, this relation is the pulsed isomorphic theorism. And using this, the diagram. Let's prove the statement 1 using the lemma. So to prove this, we can construct a homomorphism map. For example, from A to, in this case, A tensor product GM homomorphism map. How construct this map? This is A goes to A tensor product GM. If we choose the element A, then it goes to FA, defined as A tensor product, in this case GM, so check G. Then where is Gn? Where is element G? Is element Gm. But in this case, let's consider star means except the G is the element in Gm, but non-zero element, such as 1, 2, from 1, 2, 3, from m minus 1. But G is non-equal. It is not equal to 0. Okay. If you give this map, we can check. This map is clearly homomorphism. The reason is, if we, in this case, we skip, because we skip the notation R. This is G module, so this is G module homomorphism. So the reason is clear. If A plus A prime, then the result is A plus A prime tensor product G, and because of the tensor product operation calculation, this is same A plus G, A tensor product G, A tensor product G prime, and this is clearly FA, and in this case this is A. So this is FA plus FA prime. So this property is clearly additive rule is clearly satisfied. And in case of multiplication, because this is also written as RA tensor product G, but note that because this is G module and G is the clearly commutative ring. Because of commutative ring, we can say this is here. In general definition of the tensor product, this equation does not hold, but because this is G module, this equation satisfied, and this means R by definition of the tensor product F, this is R F A. Anyway, we can check the map F if we define FA is A tensor product G, but G is non-zero element, but this is clearly a homomorphism mapping. And next, we consider the natural epimorphism, natural projection A quotient MA, and its map. In this case, I say this is. We can check this is this homomorphism. So this is what is name? Okay, this is for convenience. I took this map. Take this map phi. Our claim is that MA, if MA is equal to corner phi, corner F. But in this case, this is the name is not required. If we prove this equality, then by the previous lemma, naturally we can deduct this quotient group is equal to tensor product. So check this relation. To check this, first check the relation this here. In this means if MA, X is the element in MA, this means X is denoted this MA. M is fixed number, A is for sum A in A. Then claim is, in this case, in this direction, claim is F MA is 0. It means 0 tensor product 0. The definition of the F, this is expressed MA tensor product G. Okay, and note that because the operation of the tensor product, this is equal to A tensor product MG. Okay, but note that, again note that because mg is contained to gm, this is clearly 0. And by the definition of the properties of the tensor product, this is clearly 0. So this means from this here, so xma is clearly corner F. So this set relation here is clearly satisfied. So let's prove the other side. This means corner F is contained MA. So to prove this, suppose X is corner F. Note that corner F means this is clearly the subset of the A. When the definition of the G module, rather than G module, the definition of the map, homomorphism map F. Okay. And where A comes from, A is comes G product A to A. So all of the element is X is consist of, we can say, RA for some R in integer G. If we just consider A is just 1A. 1 is the integer of the A. And then let's consider the definition of the corner Fx. It means it goes to the RA, but I already defined F map is here. So this is RA plus tensor product G, some fixed number of the G, and I want to say this is 0 for A in A. But to do this, the only method is G is fixed number, and for all elements in A, to do this, A tensor product, if with the properties of the tensor product Rg, when you consider this, the because of the property of the tensor product, we can say this, write this. And to satisfy the fx to be the 0, the only method is, when considering this is the element in Gm, Rg is 0. In the sense of the Gm, Rg is 0, just 0, and in the sense of the integer, this is the Rg is the multiple of the k for some k in integer. This means R is equal to G over mk. Of course, G is the Gm star. This means G is constant element in Gm but non-zero element. So we can divide this here. And when considering this, for some R integer, choose the G module. This is clearly should be integer. Looks like, even though it looks like a fraction, this is clearly must be integer. So mk G, mk is divided by G. Okay, our claim is X is in element in MA. It is our final claim. And so if we try to RA again, RA means when considering again the definition of the G module, this is the R sums of dA. So because R is the, in this case, mk over G, this means mk over G times. And when we consider, because clearly this is integer, we can say this is gk over m. So this element is clearly gk m a. Okay, this is element. This contains this element. Of course, this is integer. Okay, and our claim is here. MA. This so X is contained MA. I can check this property. Okay. But to prove this, our claim is K over G. This is here. This is integer. If this is satisfied, this is also integer. This is integer. So this set relation clearly satisfied. Just m is same, and another integer. If this property is satisfied, another integer is satisfied, such as OMG. If a is the integer, is clearly mg. So if we prove this statement, we can prove. And if we check this property, this means when considering this equation, R is divided by M. Okay, R M is K over G, R divided M, then K over G is the multiple, and this is integer. If this claim is true, then this means R is multiple of the M. This means MA. However, the serious problem is here. There is no need to be K over G is to be integer. So when we using this map, we can check this X is contained MA. So how can solve this problem? When considering to solve this problem, the good method is define the app, redefine the map F. Just instead, FA is tensor product. I define FA is a tensor product G, where G is in GM star when considering this case. But in this case, just define we choose here, FA is defined a tensor product 1 identity in GM. Then we can solve this problem. Check. First, we can check this here. This is no problem if just change the G instead of 1. These properties, all property I referred are satisfied. And the problem is here. When back to this here, when it comes to fx, this is clearly by the definition RA tensor product 1. I want this be 0, and by the tensor, again the tensor product properties of tensor product, this is also R1. Okay, then when considering this term, for all element A in A to be 0, this should be R is multiple of M when considering this. For some K in G integer. This means X should be written as MKA, and this means MKA, so X is clearly multiple of M, A. Okay, of course, K is integer, A is the additive abelian group. When consider the definition of the G module, Ka is clearly in A, so X is anyway X is contained MA. So firstly, if we define the homomorphism map is A tensor product 1, we can check this is clearly satisfied. This just change fix the number G as 1. Okay. Then we can check this isomorphic relation because we proved kernel F is equal to MA, so we can conclude that AMA is isomorphic to A tensor product GM. And the second properties, let's say this here. G, if we substitute A Gn, then Gn tensor product Gm is clearly Gn quotient MA, and we see the definition of the tensor quotient group. This is clearly GMN. And next theorism I want to say is the universal property of the tensor product. So Let's record universal property in lecture 3. An object in category C said to be universal. For each object C in C, there exists only one isomorphism I from I to C. For example, when we consider pre-object, the definition of the pre-object, we can say this is universal properties, because for each object A is given by the definition of the pre-object, there is a unique morphism from F to A. Let's see a definition to prove the universal property of the tensor product. It's canonical linear map. Middle linear map means A, B, over ring R. This is the right R module. This is the left R module. And define middle linear map. In the previous lecture, middle linear map, I referred middle linear map says a product B to a tensor product, this pair goes to the tensor, then the map I is called canonical middle linear map. So this means AB goes to BR map I. This is a tensor product B, and when you choose this element, this goes to defined as a tensor product B. But note that because this is the middle linear map, following it or satisfy if I1 plus A1 A2 B is IA1 B plus IA2 B. In case of B, this is also satisfied the linear property, and IRA B is equal to I A. Of course, in this case, A is the right R module, so this is AR. B is this right side B. This means just we change the tensor product. This is just some properties of a tensor product. For example, in case of this example, the map I is defined here. A1 plus A2 tensor product is equal to, this is A1 tensor product B and A2 tensor product B. And another remaining is also written as the expression as the tensor product. Now let's our fundamental protagonist, one of the protagonists, universal property. Let A and B be over a ring R. This is a right R module, left R module, and C be an abelian group. If G, a product B to C, this is G, is the middle linear map, then there exists a unique group homomorphism G bar by G from here such that this is canonical middle linear map I referred. These commutative relations satisfy. So a tensor product B is uniquely determined up to isomorphism by this property. From this here, we can check this is universal property. So for any object C is given, just using the definition, for any object C is given, there is a unique morphism, unique object A R B, okay, only one morphism, okay, only one morphism from here, A tensor product RB to C. So let's prove the statement, the universal properties. I will use this lemma, but this lemma is so familiar because in the previous slide, in order to prove the tensor product about the integer, I introduced this lemma. So I proactively use this lemma in order to prove universal property. So let's start the proof. First, consider the following diagram. When we consider A, B is the basis and F is the pre-abelian group which is generated by AB. Then for any group element in C, when considering these three objects, there is unique homomorphism G. For convenience, I put G1. Unique homomorphism such that following diagram is commutative. Okay. And we can consider this here. In order to prove this, I'll consider homomorphism map F to C. This is clearly homomorphism. And we can consider vector group F over K. This is, if we consider some others generated by A tensor product B, this is FAB. And of course K is the generated the tensor condition. So this means I want to say this is just A tensor product B. When we consider this lemma, the remaining thing is here. I want to say this map, our claim, this from F quotient K, so this tensor product, from this tensor product to C, there is unique homomorphism. I want to find unique homomorphism G bar. This is here. But if we use the lemma, if just define here, this is unique homomorphism. So we can find unique homomorphism mapping, which when considering A, B is generated A, B, FC is the this diagram. And when we consider the universal, in the sense of the universal properties, this is the canonical middle linear map, and there is unique homomorphism G such that following commutative relations are satisfied. This blue arrow means here. Okay. So in order to check these universal properties, if we just define the map G A tensor product B goes to C, which means this is the AB plus K in the quotient element in the quotient group. This goes to just define in this case A B okay, G1AB considering homomorphism map. This is clearly unique homomorphism mapping. So the map from here is unique. This means I say the properties, this map is unique. And in order to check the commutative relation, just check this. Gi, this is G bar Gi AB means just bar G AB. No, we can define this as tensor product middle linear map when consider. Okay, we can define the middle linear map. So this is G tensor product AB. Okay, and we can say this GI means this here, this blue arrow, but this blue arrow is the same as the green arrow from A product B to C. For convenience, if we try to disguise the G, and this is already G, okay, then this is G, in this case AB, for all AB. So from this here, GI is equal to G, and this is unique homomorphism. So our claim is finished. The previous example is the general definition of the tensor product. Of course, if the A, B are commutative ring R, these properties are so satisfied. In this case, the map I, term of the I is changed canonical bilinear map instead of middle linear map. And under the bilinear map sense, universal properties are so satisfied. Now, let's talk about split exact sequence on the tensor product. As we saw, the projective or injective module, from projective or injective module to the dual module, split exact sequence properties always exist. Of course, of the tensor product, split exact sequence property exists. So let's read the theorism. 0. This is if this is split exact sequence of left arm modules and D is the right arm modules, then following sequence is also split exact sequence of abelian groups. However, in order to prove this split exact sequence, it is better to show this lemma. If A, B, C, 0 is exact sequence, then this tensor product is also exact sequence. This means, by the definition, image identity D to F is the corner identity D tensor product G, and this is if claim is here, and the identity tensor product G is epimorphism. If we succeed to prove these properties, this to show that this is split exact sequence is clearly trivial, because this is the split exact sequence. Some of the properties to fulfill the split exact sequence property, because split exact sequence is also exact sequence, and the remaining, if we finish this proof, the remaining is just here. This means here. To show the split exact sequence, we just find R module homomorphism from D tensor product C to D tensor product B. So we just find the map identity G prime, but when considering the assumption G is the epimorphism, or in this case also we can check G is clearly epimorphism. Okay, so because this property, we can easily to find the inverse map from here, such that in this case, to consider the direction GH. Okay, so it's a condition identity G prime identity DG, this here to this here, this is identity the tensor product RC. So our main gist is this: check the split exact sequence is clear work, but remaining is this work is little requires some our thinking. So let's prove the statement. To be tensor identity tensor product G is the epimorphism is your exercise. I prove this equality. So in this case, choose the element. In this case, identity F. So when we choose the element is clearly the tensor product B, image identity F. identity F. This means there exists A in A such that identity, just definition of the image A D, okay, in this case D tensor product A, it means identity map goes to identity, and FA, and this is D tensor product B. So anyway, the value of B depends on the function f. Okay. And next we try to identity. If we try to identity goes to identity the tensor product G via identity product tensor G, this map goes to here, because in this case corner G is image F is corner G, so all element in B is generated by the image F. So this is clearly this B is clearly corner G. So this is clearly D tensor product 0. This means this is just 0. Oh, this means the tensor product B is corner identity tensor product G. Now let's consider the other direction. In this proof, we also used the lemma. This is already the proof in this lecture. So the first thing we should do is construct the homomorphism map here. In this case, let's consider this here. When considering exact sequence, this arrow is always connected by homomorphism, R-module homomorphism. So in this case, we can think the tensor product R, B, the tensor product R, C is clearly connected homomorphism. The name is identity G. And consider, let's consider this here. The tensor product RB image identity F. Let's consider image. By previous theorem, we can prove this relation. Okay. For identity 1G means here. This means by thinking this lemma, this means there is unique homomorphism alpha. Unique homomorphism alpha such that between, what is homomorphism? Between this here. Okay. But our claim is, in fact, in the other direction, this direction, it means if this direction is satisfied and this direction is satisfied means this is equal to here. To be equal, if and if condition, to satisfy equal if and if condition, this map is isomorphism. So our claim is alpha is isomorphism mapping. Then our claim is finished. So to check this, our claim is here because anyway alpha is unique homomorphism. So we can check that alpha is a monomorphism and alpha is epimorphism. So to do this, we can use some theorem or theorism in the set theory. If we check f AB, HAB, and BA are functions, then if G composition F is identity, then F is injective. And HG is identity B, H is surjective. Because our claim is, in this case, F and H is the same if we prove that G, F identity A and F, G identity B satisfied. We can check that F is bijective. So this means we can let's construct the map beta. So to do this, our claim, if we well define the map beta, then we can check alpha beta. This is epimorphism condition. Alpha beta beta goes to alpha is identity homo RDC. And in this case, beta alpha is identity here. This is so wrong. So if we can check this theorem, our proof is finished. So to prove our claim, let's consider we can construct some new map from here, this diagram. I'll put D product C. I put D product C, and if we map this Cartesian product is given, we can think naturally given we can give the canonical middle linear map. For convenience, I'll put this map is beta bar for the notational rule. And let's consider then let's consider this map beta. Our claim first to whether it is well defined or not, the map beta. Instead, we can check this is clearly well-defined map. We can check if the map beta is well-defined, the map beta bar is clearly automatically well-defined map. So we can notice the map beta. So how can we define the map beta? In this case, let the map to here to be well-defined map. This is clearly coordinate and beta DC. We can define beta DC if we consider this is, if this map is the pi. This map finally goes to here, and if we consider this side, this map via pi, this set is via pi goes to here. So we can define this is pi d tensor product B. Our claim, we can just define this map. Our claim is that this map is well defined. The problem of well-definedness is from here. Let's consider the element, the tensor product C. Then because we can say G is epimorphism, clearly there exists B element in B such that G B is equal to C. Okay, so map C is depend on the map C. If we consider this map, C is depend on the value GB. But note that this is unique, not unique morphism, unique element. So we can choose clearly there is possibility another element but not equal to B, such that GB prime is equal to C. So clearly GB prime is equal to C. In this case, we can, to be well-definedness, we can check if the map pi is well-defined. Clearly, this is written as B prime. And this tar means we can say this tar is written as here G B minus B prime is 0. This means B minus B prime is contained kernel G. But anyway, by using the definition, the exact sequence, this is image F. This means there exists element in A, in this case kernel G, image F, okay, image F, such that F A F B minus B prime is equal to of FA is equal to B minus B prime. Then we can conclude this equation because when we calculate pi the tensor product B means the tensor product B is written as F A B prime. This means the tensor product FA dB prime and the tensor product FA is clearly image identity F, and this is corner the previous direction identity G. So if this map goes to here via identity map G, this is clearly 0. So this result is clearly 0. So this is vanished. This remains the tensor product B prime. Then we can check the map beta is well defined in this map. Automatically, the beta prime is clearly well defined, and when considering this here, by universal property satisfies. It means there exists unique beta bar such that beta is expressed beta bar I. To get the final result, we can check epimorphism and monomorphism relation. So because beta bar is clearly well defined, we can check, for example, alpha, beta, and in this case the tensor product C. This means alpha, because when goes to the beta bar, then pi is surjective. This is written as the tensor product B. And when goes to again alpha, this means the tensor product GB, and this is equal to the tensor product C. So this means alpha is epimorphism. And similarly, we can check beta alpha is identity home here. So this means alpha is monomorphism. So because alpha is unique homomorphism, and we can prove alpha is epi and monomorphism. So this and this isomorphism relation, and by the previous lemma I continuously referred I deleted here. Anyway, by the lemma image identity app is equal to corner identity G. Our last slide is the joint associativity. I'll not prove this statement concretely, but this is useful. This is important when you consider the when someone considers the functor. When you study the functor, this come up in this adjoint name as adjoint associativity. So theorism is here. So home as this has isomorphic relation to here. Traditionally, to check the isomorphism, we construct the map. So to the map to connect this here, connected this map, we consider F. F is contained ARB, this home AR tensor product B to C. This is clearly F. And if we consider the map via F, of course we can check alpha F. We must check alpha F to be well defined in this home RA, home SBC. Okay. And if we consider the domain is A, we can put this A. The check thing is that alpha F A, if we consider the map A, substitute the element in A, then this element should be home SBC. We also check, maybe check this here. And if this map is because this map is home SBC, new attachment B is also required. If we believe the map is the well-defined map, so this map is contained in the set, you check this set relation. Then, if we believe that it's well-defined, the final element is in C. This is defined here. F tensor product AB. This is clear element in C. So if we define this map, we can check this isomorphic relation. Then, to check the isomorphism is clear. Just check this alpha F G is alpha F alpha G. To check these monomorphism and epimorphism relation, we reuse the lemma here. So this means construct a new map beta home R A home SBC goes to home S A tensor product B C. If we choose the map G, This means this is element, so if we element in A, GA is the home BC. This means GA is the map from B to C. Then if it goes to the map beta, and if the map is well defined, beta G is clearly contained in this home SA tensor product BC, and this element consists of A tensor product B. And then if we define this goes to C, so the result is if we consider the element in B in map GA, it goes to clearly GA B is clearly in C. So using this here, let's define this map is GA B. And if we define the map as we did, we can get alpha beta is equal to identity. This is beta goes to home R A home SBC, and beta alpha is identity home A tensor product R B C. So from this here we can get alpha is 1 1 and on 2 map. So from 1 and 2, this isomorph we can check the isomorphic relation.